Welcome to the solutions to problem set number 14, where we discuss isomorphisms. So in exercise 1, phi, again I say phi, not phi, hope it's the correct pronunciation. This phi is an isomorphism between groups G and H. By definition, this means it is a bijective homomorphism. So another way to write this is G is isomorphic to H, and now some of the properties, or actually all of the properties of G can be transferred to H, and this is what we're going to show in this exercise. So first of all, why is the cardinality of those groups the same? Well, simply by definition of bijectivity, because in the finite case it is simple. If, say, G has 8 elements and we have a bijective map to H, then of course H also has 8 elements. So clearly they are of the same order. But in the infinite case, having the same cardinality actually means that there is a bijective map from G to H. So this here has nothing to do with the fact that phi is a homomorphism, but simply that phi is a bijective map. And then of course, we know that the dihedral group of the regular four-gon or the square has 8 elements, and this is less than 4 factorial, which is 24, which is the order of S4, hence those groups cannot be isomorphic, because if they were isomorphic, they would have the same order, which they don't. So this is the first indication when groups are not isomorphic, simply when they are of different orders. Okay, part B. Very important, it is not enough to have the same order. There are groups of order 8 that are not isomorphic, so it's not enough to have a bijective map. It also needs to be a homomorphism. If we have a bijective homomorphism between groups, then they have the same group table. Of course, this only makes sense in the finite case, otherwise we can't write down the group table. So why is that? Because, for example, I know here that B composed with A is this element here. Now I can write down the elements of H. It's the same number of elements, we just established that, and because phi is bijective, I know that this element here can be written as phi of some element here, and now I take the order here to be exactly as here. So I, if necessary, reorder the elements such that this element here is the image of this element under phi, and this here is the image of this element under phi. Then, what do I get here? So I take a look at this element composed with this one, same as here in this group table, only that the operation now is hard. So H hard G is by definition of G and H, phi of B, hard phi of A, and now because phi is a homomorphism, this can be written as phi of B circle A, so composition in G. So we see that the group tables are exactly the same because this element here gets mapped to exactly this element here. And this uses both properties of phi, namely that phi is bijective, which we used here, and that phi is also a homomorphism, which we used here. So isomorphic groups have the same group table. So from the standpoint of classifying groups, they are the same group, only the elements are named differently. This is the idea of an isomorphism. So exercise C shows that if G is abelian or commutative, then so is H. So we cannot have an isomorphism between a commutative and a non-commutative group, even if they are of the same order. So we take 2 arbitrary elements of H, and now I simply write dot instead of hard and circle. So this is operational composition in H. Now again, because of this argument, I know that G and H can be written in this way here, actually uniquely in this way because phi is bijective, but that's not important, surjectivity is enough. I can write G like that and H like that, and now because phi is a homomorphism, this is the same as phi applied to AB. But now G is abelian, so here I use that G is abelian, here I use that phi is a homomorphism, and for the, I don't know, 20th time, if you're taking notes, please write down this stuff. Right above this equality sign, we use that phi is a homomorphism. Here we use that G is abelian, and so on. I do not write it down all on the blackboard. So, but now again, because phi is a homomorphism, this can be written like that. So we end up with H composed or multiplied with G. So this shows, because G and H were arbitrary, that H is an abelian group. And as explained before, although those groups have the same number of elements, 6 and 6, they cannot be isomorphic because the integers mod 6, because the integers mod 6z or z sub 6 are an abelian group, and this one here isn't. Dihedral group of the equilateral triangle is non-commutative, so we cannot have an isomorphism, because if they were isomorphic, then both groups would have to be abelian. Okay, part D. We take an arbitrary element of H. Then we know there is a unique element of G such that G can be written as phi applied to this A. Now A has some order. We call it n. And now we're going to show that then this G also is of order n. This proves the claim in part D, because then we know, because of the one-to-one correspondence, if I have 17 elements of order 5 in this group G, then I will find exactly the same number of elements of order 5 in this group H. That's the claim. So, and remember, the order is the smallest integer such that a to the nth power is the identity of the group. Okay. So first of all, we take a look at G to the n. This is phi of a to the nth power. Now, because phi is a homomorphism, I can pull this n inside, because, for example, phi of a squared is phi of a composed with phi of a. This is phi of a composed with a, because phi is a homomorphism. And inductively you can show that this is true. I think we also did that on problem set number, I don't know, on some previous problem set we proved this actually for all integer powers. Now, because a is of order n, a to the n is the identity, and we already know that a homomorphism always maps the neutral element to the neutral element of the other group. So we end up with the fact that G to the n is the neutral element of H, but we are not done yet. This only shows that the order of G is a divisor of this n. We proved that a while ago, but it could be smaller. So let's take a smaller number, a smaller natural number than n. Then we have G to the k is, by the same argument, phi applied to a to the k. So, and now we know that a to the k cannot be the identity because k is smaller than the order of a. And we know that phi is injective, meaning that its kernel is a singleton set consisting only of the identity. So if a to the k is not the identity, it cannot lie in the kernel of phi. And by definition, this means that this guy cannot get mapped to the identity. And this taken together shows that n actually is the order of G. Here it could be, the order could be smaller, but this shows n is the smallest natural number such that this holds. So as explained before, isomorphic groups contain the same number of elements of a given order n. N was any natural number here. Okay, and why does this prove that these two groups cannot be isomorphic? This here is the Klein 4 group, and we know that all of its elements are of order 2, except for the identity, of course, which is of order 1. Here, not every element is of order 2. For example, I take the residue class of 1 mod 4. So, and here we do not write 1 bar to the power of 2, because this is an additive group. We write 2 times 1 bar. So G squared would be in additive notation this here. This is 2 bar. This is not the same as 0 bar, because 2 and 0 do not lie in the same residue class. And also 3 times 1 bar is not 0, and for the first time 4 times 1 bar is 4 bar, which then is 0. So the order of 1 bar, or the residue class of 1 in this group, is actually 4. And there we do not have a single element of order 4. Therefore, those groups cannot be isomorphic. So this here are both abelian groups with the same number of elements, but they are not isomorphic. Okay, so using A, they could still be isomorphic. They have the same number of elements. Using C, they are both abelian, so they could still be isomorphic, but with part D, we see that they cannot be isomorphic groups. Okay, and another proof would come from part E, because this here is a cyclic group, because as we've just seen here, 1 bar generates all the elements of this group here, whereas this here cannot be cyclic, because if I raise any element here to the second power, I get the identity. So there's no element that could generate this group here. Okay, so part E can be written as follows. If G is cyclic, generated by an element G, then so is H. And what is our guess for the generator? Of course, it is phi of G. So we will prove that this here generates H. Okay, to prove this, we take an arbitrary element of H. Then, because phi is bijective, we know that H can be written in a unique way as phi of A. Here again, surjectivity would be enough, because we simply need that it can be written for some A. It doesn't have to be unique. But we know that this A here lies in G, which by assumption is cyclic. By definition of cyclic groups, this means exactly that A can be written as this generator raised to some integer power k. Okay, but now that means that H is phi of A, which is phi of G to the k, and again by exercise number so-and-so on problem set, we prove this for any integer power. And this shows exactly what we wanted to show, namely that H can be written as some integer power of phi of G. This means exactly that phi of G is the generator of the group H, and we are done. Another way to put it, this here clearly is an element of the cyclic group generated by phi of G. By definition, this set consists of all the integer powers of this element. So we know that H is a subset of this here, but clearly this is also a subset of H, because this is a subgroup of H by definition. So this shows that H is indeed cyclic and generated by phi of G. Okay, and to be perfectly fair to all the new students or real beginners, let's just write it down. So this here shows if H is in H, it also lies in here. So H is a subgroup of this here, and clearly this is a subgroup of H because it consists of elements that lie in H by definition, all those powers. So this taken together shows that they must be the same group. So, and as I've said before, this again proves that these two groups cannot be isomorphic, because this here cannot be cyclic. All the powers end at 2 and become the identity. So the highest exponent is 2 because any element here squared gives me the identity. So I cannot end up with all the elements if I take the power of any element here. Whereas this group is clearly cyclic, generated by the residue class of 1 mod 4. And here again, if this was not clear enough, if I take a non-identity element, G, in this group, then G squared is always the identity. We proved this here for this Klein 4 group. Then G to the power of 3 is G, clearly, because it is G squared times G. Then G to the fourth power is E times E, so E. So all the powers here simply give me E or G. So I cannot end up with 4 elements with the whole group. This shows that this group is not cyclic. And maybe I should have used additive notation as well. Element in here, for example, is 1 bar, 0 bar, this tuple here. If I take this times 2, I end up with 0, 0, which is the identity in this group, and so on. All right, exercise number 2. Is there a group G with a proper subgroup, meaning this is a subgroup that is not the whole group, such that H is still isomorphic to the whole group? At first glance, this obviously seems wrong, because in exercise 1a, we showed that isomorphic groups have the same order. So this clearly cannot be true for finite groups, because in the finite case, if I have a proper subgroup of, say, a group with 8 elements, this cannot have 8 elements. But if they are isomorphic, they have the same number of elements in the finite case. So we have to look for an infinite example. And actually we already know that, because this here is a subgroup of the integers, which is clearly a proper subgroup. These are all the even numbers, not the same as all the integers. But this map here is an isomorphism. If I send an integer to 2 times itself, I end up with an even number, so this is well defined. And this clearly is bijective, because this is its inverse. This looks strange, but remember, we are in the even numbers, so if I divide an even number by 2, I also end up with an integer every time. So this is a well-defined map, and those are clearly inverse maps of each other. So this is a bijective map. Is it also a homomorphism? Well, yes. Because what is phi applied to this sum here? It is 2 times z plus w, which is by the distributive law, 2 times z plus 2 times w, which is exactly phi of z plus phi of w, showing that it is a homomorphism. Be aware that we have 2 additively written groups. The operation is written as plus, not times or dot or whatever. So this is the homomorphism property for this phi. So we have a homomorphism that is clearly bijective. That means that these groups are actually isomorphic. And it does not contradict exercise 1, of course, because we proved this there, because those 2 sets have the same cardinality by definition for infinite sets. 2 infinite sets are called of the same order. I don't know, of cardinality maybe is better if there is a bijective map between them. And there is. So there are as many even integers as there are integers even and odd taken together. As strange as this sounds, we already discussed this on problem set number 12. All right. Exercise number 3. On problem set 4, we convinced ourselves that this set here, the rational numbers, with the exception of -1, with this strange operation here, a circle b is a plus b plus a times b, is indeed a group. Here we are going to show that this is nothing but the multiplicative group of the rational numbers. So Q star is the set Q without 0, and the group operation is simply multiplication. So from the standpoint of group theory, those two groups are the same. So let's check that. First of all, the image of phi clearly lies in here, because if I add 1 to any of these numbers, I end up with any rational number except for 0. So clearly the image of this map is a subset of this here, because I cannot end up with 0 because -1 is missing in my group G. Okay, clearly this is a bijective map, because the inverse map clearly is simply subtracting 1, so phi inverse going from here to there would be given by B gets sent to B minus 1. So bijectivity is clear. So all that is left to check is phi indeed a homomorphism? So we need to check that for any elements A and B in this group, is this true? So for all A, B in G should be written here. So, but this is a simple calculation. The left-hand side gives me this here. Phi of A circle B is this by definition, and phi simply adds 1 to the number, so I end up with that. The right-hand side is this here. This is multiplication in Q. So, and now simply applying the distributive law shows me that this here and that is the same. I'm being a bit lazy now because it is clear. So we have found a homomorphism that is bijective from this set to the multiplicative group of the rational numbers, and this shows that this strange group here is nothing but the multiplicative group of rational numbers. Okay, now there's still one question open in exercise number 3. Is it possible to find an isomorphism between the multiplicative group of the rational numbers and the additive group? They might as well be isomorphic. Well, no, this cannot be true, because this here is Q without 0. This clearly has order infinity minus 1, which is less than infinity, which is the order of Q. Therefore, they cannot be isomorphic, because an isomorphism would preserve the order. Done. Nah, okay, I'm just kidding. This is clearly no valid argument here. So you have to think about this. It's not so easy at first glance. But then, if you remember exercise number 1, where we showed that certain properties get preserved in isomorphic groups. For example, if we take a look at the element -1 here, then -1 squared is 1. And -1 itself is not 1. So we have an element of order 2 in this group here. If they were isomorphic, then there would have to be at least one element of order 2 also in this group. But what is the order of a rational number? So here, this is additively written. So we write n times A over B. And for this to have order n, we would have to end up with 0, because here the neutral element or the identity is 0. So in multiplicative notation, we would have g to the n, or q to the n, because we're talking about the rationals, would have to be 1 here in this group. But here, additively written, this translates into this. The 1 corresponds to the 0. Q is now this fraction a over b, and to the power of n we write as n times. But clearly this is not possible. If this here is not 0 itself, so this has to be a non-zero element, there is of course no integer such that this here would be satisfied. So here we have an element of order 2, here not. Therefore, the no was true, but the argument here of course was a joke. They are not isomorphic.